Hello everyone. In last lecture itself I started design of welded joint subjected to combined stresses, or you can say design of welded joint subjected to combined loads. Today also I will start from the remaining part of that topics. First of all, I will discuss about that last problem which I was discussing related to welded joint subjected to bending moment. Then how to design that welded joint, that related thing I was discussing. So, first of all I will discuss about that problem again briefly. After that actually I will discuss about the following topics which is related to today's lecture, that is welded joint subjected to combined loading. Here I will solve one problem related to welded joint subjected to torsional types of moment as well as bending moment if it is subjected, then how to design that welded joint. Then I will discuss about the very important topics, that is related to design and analysis of welded joint by the concept of shear flow. Especially I will use design of flat welded structure based on this shear flow concept. There I will discuss about what is shear flow, what is its importance, how we can design a welded joint subjected to different types of combined loading, and how we can find out this resultant shear flow once it is subjected to different types of combined loading. And at the end I will also solve some problem based on what it is called concept of shear flow, especially in fillet weld. So, I fillet weld because fillet weld have a wide application in the in manufacturing industry. So, this concept we can use both fillet as well as butt weld, but especially we will concentrate more on fillet types of weld joint. So, first of all I will discuss about the last day's problem which I was discussing. There I was already discussing about the problem related to welded joint subjected to bending moment. The problem statement was like this. I have already solved this problem in last lecture itself. Again little bit I am just refreshing those concepts, because that will be required in subsequent topics, that is why I am just discussing this thing. So, let us say 50 millimeter diameter circular beam. Why it is beam? Because here the load is acting transverse to the axis of this body, you can say, that is why it is called beam. It is welded at a support by means of a fillet weld as shown in figure. You see here this fillet welding is done, and at the end you see the load is applied 10 kilonewton. So, determine the size of the weld. We need to design, that means we need to find what should be the size of the weld, that means leg length, you can say leg length, you can say is that we need to find out, so that what happens, it is able to support this 10 kilonewton load. So, here the permissible shear stress of the weld is given as 100 MPa, that means this is the allowable stress. This much maximum stress we can applied in this welded joint, that is called allowable stress. I have already told you what is allowable stress in detail. Okay. So, we need to solve this problem. So, how to solve this problem? For solving these problems I have already discussed in last lecture itself, because let this is a transverse load P. Once for this transverse load case, that means for this beam case, we first shift this load P from this location to CG of this weld, you can see. Once we shift this load from here to here, we know there will be creating a bending moment. How the bending moment is creating, this bending moment how it is acting, that you can see depending upon the loading direction, it is creating a bending moment which is, that means clockwise in direction, because P is downward. So, it is with respect to this base it is clockwise, you know this thing. So, this bending moment and there will be a equivalent load P. How it is coming, you know. Then also little bit I am just discussing this thing. Let this is a body, there is a load P. Then if we shift this load P from here to at a distance L here, let us we want to shift this load P here, okay. Then we want to share this load P here, but what happens at this, let this is edge A, this is edge B. At edge B there was a load, but at edge A there is no load. So, P due to this P at edge A there is no load. So, we applied a load, we apply a load P, as there is no load. So, we need to apply a opposite directional load P, which is opposite to the direction of this applied load P. Then what happens, you can say here the resultant load will be this plus P minus A will be 0, correct. Now, this we can write, this is equivalent to, you can say this is equivalent to, we can write as this is one load and this is another load, plus you can write there will be this, correct, because this load once we shift from here to here, then what happens, there will be, you see this there will be a you can say two parallel load will be there with a distance E, and there will be another load, applied load, the P also will be there. This way you can combine, you can write like this. Now, these two parallel load will create a moment, or you can say couple. So, this couple will be, you can write as P into distance between two force. This is actually your bending moment, you can say MB, and there will be another force which is remain as it is, that is P. So, there will be plus another force will be there P, which is similar to the force at the end B. This you should keep it in mind. So, this is the concept generally we use here. So, here we have written like this. So, this couple and force we can separate into this way. I have already shown these things here, okay. There will be a force and there will be a couple. Now, this direct force will create a, you can say create a direct shear. Here this direct force will create a shear force, whereas this bending moment will create a what it is called bending stress. So, you see this direct force will create a shear force tau, it is represented as tau 1, and this bending moment will create a bending stress sigma b. Always you should keep it in mind, this tau 1 is generally acting along the direction of the this you should keep it in mind, this is always act along the direction or along the plane of the you can say throat area, throat cross sectional area. It is a shear force. So, let us consider the throat area. So, it is a shear force. So, if it is written in terms of a state of stress condition, so you can say this will create a shear stress which is looks like this. Let us consider this will create a shear stress which is look like this. This is called primary shear stress. Okay. This primary shear stress, you know these things, this is generally balancing types of shear stress. Okay. Now, this is primary shear stress, it is acting. This is due to direct force P. So, this tau 1 already I have discussed is equal to P by, you can say total cross sectional area or throat cross sectional area of the weld. I have already discussed this thing, and due to this bending moment there will be a stress sigma b which is generally which will be acting or which will act perpendicular to the throat cross sectional area. So, always you should keep it in sigma b is acting perpendicular to throat cross sectional area, this you should keep it in mind. So, along the throat area if it is tau 1, then perpendicular to the throat area it is state of stress will be written as sigma b like this, this you should keep it in, sigma b will be like this. Now, if a state of stress have a shear component tau 1 and sigma b component that means normal component sigma b, then we know the resultant shear or maximum shear stress due to this state of stress. State of stress means already I have shown, which is generally it is tau 1 and there will be a bending stress sigma b, then maximum shear stress, this we can get from the concept of strength of material. So, I am not going in details how to get these things. So, we know this formula tau max generally sigma x minus sigma y divided by 2 square plus you can say tau square shear stress component. So, here generally you can see there is only one normal component, okay. There is only one normal component, this you can say, and there is only one shear component. So, you can write as this is equivalent to sigma b by 2, because one of the component sigma y will be equal to 0 plus tau 1 square. Now, last lecture already I have discussed these things, what is sigma 1 and sigma b. So, sigma 1 generally we got as last class already I discussed, that is generally we got as directly here I am writing sigma 1 square is generally 63.66 divided by t whole square, and this sigma b we got generally from the pure bending theory. We know sigma b by y is equal to m by m b by I. Here I generally I x x, always you should keep it in mind, because about x axis generally you can say about horizontal axis generally this bending moment is acting, because its direction is generally you can say towards the direction of x x, that is why we need to take I x x component. So, from here you can get sigma b is equal to m b y by I, and here we should consider the maximum bending stress. So, this y should be you can say radius of this beam you can say. So, radius of this beam r. So, based on this formula I x x last lecture already I discussed in details. So, we got sigma b equal to, directly I am putting these things, 1018 divided by throat thickness 0.59 divided by throat thickness, and on 2 is there whole square. Okay. So, based on this formulation generally this tau max, for designing purpose generally this tau max we will use to find out the dimension, or you can say throat thickness of this weld specimen. For finding out this throat thickness, this tau max we need to equate with allowable shear stress. So, which is given as 100 MPa, already it is given, because this 100 MPa is already given. So, this unit, left side unit is also Newton per millimeter square, the right side unit also Newton per millimeter square. Why? Because MPa means 1 MPa is equal to 1 Newton per millimeter square, always you should keep it in mind. So, from here generally by using this relationship we can get T is equal to 5.13 millimeter. Now, we know that size of the weld means its leg length. Size of the weld is equal to you can say leg length H of the weld. So, this we can write. So, here size of the weld H is equal to you can write as 5.T by 5.13 divided by you can say 0.707. So, this will give you a value which is equal to 7.26 millimeter. So, generally you can consider this is the size of the weld itself, because if you will consider this thing it is okay, but what happens if you take little bit higher side, that means next full digit number, then what happens, you will be further more safer side, that you can say, but it should not less than this age value, this you should keep it in mind. So here you can consider this age is approximately equal to your 8 millimeter. This is your design size of the weld. So this I have already discussed. So now we will solve another problem. So now we have got the idea about concept of torsional types of moment as well as concept of bending moment if a structure is subjected to, then how to find out the resultant shear stress and how to find out the resultant torsional you can say shear stress, that concept already we got. Now we will solve one problem by combining this two stress component. For solving this problem, just I am just showing a problem here, you can see. So here the problem statement is like a circular shaft, you can see this is the circular shaft whose diameter is 50 millimeter. So here we will solve the problem. So during reading itself we will just see what are the different information actually given. So given data that I am writing here. So here diameter of the shaft is you can say given as 50 millimeter. It is welded, you see, by means of a fillet weld as shown in figure. So this is actually welded in a support, you can say, which is subjected to a combined loading. Combined loading, that means a transverse force P is equal to 10 kilonewton, it is subjected. This information is given, you can see here P equal to 10 kilonewton, as well as here MT is given as 2500 Newton meter. So here torsional moment MT is given as 2500 Newton meter. This Newton meters, if you convert these things into Newton millimeter, so 10 to the power 3 it will be multiplying with this. So this will be Newton millimeter. This you should keep it in mind. Okay. Now determine the size of the weld. Here also we need to find out what should be the design size of the weld is, so that it can sustain this transverse force P as well as torsional moment MT. So here your allowable shear stress is given as 100 MPa. Always you can see here we used to provide the permissible shear stress or allowable shear stress. Why? Because most of the cases generally failure is occur at throat area in shear mode. This you should keep it in weld structure. That is why this shear stress generally we consider as a design criteria for fillet types of weld. This you should keep it in mind. Now here we need to consider here already another information or data is given as the length of the shaft is given as, so length of the shaft L is given as 200 millimeter. So this information are given. So here we have already I have idea 1 what it is called primary shear stress tau 1 due to what it is called bending case, that is equal to your P by A. We also have idea sigma B is equal to M y by I, here I x x generally. If we consider this is our z axis and if we consider let this is our x axis and this is our y axis at the weld, then generally here always you should keep it in mind, here we need to consider I x x and y we need to consider as d by 2 or you can say r of the radius of the shaft. This you should keep it in mind. This is due to direct load P. Apart from these things, we also know there is coming another stress or shear stress which is due to MT. let that is I am representing is tau 2. So, this tau 2 generally you can write as m t r divided by polar moment of inertia j. How it is coming? I have already explained in details during the concept of pure shear case, because this tau 2 generally used to come tau by you can say r is equal to you can say m t by j is equal to your g theta by L. This idea is very well known to you. This is generally a theory of pure you can say torsional case. These types of relations generally we used to get actually. So, this concept generally we will use here. So, here first of all we will calculate what is tau 1. So, tau 1 generally we will calculate as P by A. So, we have already calculated these things in previous lecture itself. So, here generally 10 kilonewton means 10 into 1000 Newton divided by area is you can say 2 pi r into throat thickness. Here let us consider, I am writing here throat thickness we are considering equal to T. Okay. So, this will give us a value which is equal to you can write as 63.66 divided by T, its unit is Newton per mm square. Everything I am putting in terms of millimeter, this you should keep it in mind. Then what is our sigma b? So, sigma b generally I have already written these things, that is your mb into r, it will be mb r divided by you can say Ixx. So, last lecture itself I have shown what is Ixx. So, mb generally you can say length of the that means shifting length of the load, here shifting length of the load equal to length of the shaft itself into your P. So, you can say here P into L is your mb and here r is 25 millimeter and Ixx already I have shown you how to calculate, that is generally pi t r q. So, if we put the values, what we will get 10 into 10 to the power 3 is our Newton load, transverse load, L is 200 millimeter into 25 divided by pi into T into r q is 25 to the power cube. So, this will give us a value that is 1018.59 divided by T, its unit also Newton per millimeter square. So, this two stress due to you can say transverse load P, one is primary shear stress, you can say this is called primary shear stress. This is act generally along the plane of the throat area, this you should keep it. This is a shear stress, primary shear stress, and this bending stress which is generally used to act perpendicular to throat area, this you should keep it in mind. So, another shear stress also will be there due to what? Torsional moment, or you can say torque, that is generally create a shear stress that also will act along the throat area, this you should keep it in mind. So, torsional shear stress will be, you can write torsional shear stress tau 2 we can write as m t r divided by j. So, we know these things mt equal to 2500 Newton meter. So, this will be Newton millimeter. So, we are multiplying with 1000 mt, r is your 25 and j also I have shown you in last lecture, that is actually 2 pi t, you can say r q, because this is equal to your I x x plus I y y, because this j polar moment of inertia is I x x plus I y y. So, in case of circular section, due to symmetry, we know I x x is equal to I y y. So, this j is equal to, you can write as 2 into 2 times of I x x. So, this is already very well known to you, I have already explained this thing in last lecture itself. So, from here tau 2 you can get as 2500 into 10 to the power 3 into 25 divided by 2 pi t into 25 to the power cube. So, this will give us a value which is actually 636.36 you can write, divided by T Newton per mm square, correct. So, this is the torsional shear stress. So, you can say this torsional shear stress also will act along the, this also will act along the throat cross sectional area, throat cross sectional area, this you should keep it in mind. It also acts along the throat cross sectional area, this you should keep it in mind. So, here the state of stress, how it will be looking like, here the state of stress will be looking like, you can say. So, let us, this is our z axis and let this is our x axis, horizontal axis is x axis and let us, this vertical axis is let us y axis. So, here generally you can write the state of stress will be, two component of the stress will be shear stress. So, that is why shear stress have two component. So, which will act along the throat cross sectional area, which is shearing in nature. So, here it will be tau 1 plus tau 2, here also tau 1 plus tau 2 resultant shear stress, and there will be a, you can say, bending stress which will act perpendicular to the throat cross sectional area, you see. So, this is normal component, you can say generally it is acting perpendicular to the throat cross sectional area, you should keep it, and this primary and you can say torsional shear stress will act along the throat cross sectional area. So, so it will looks like, a state of stress will look like this, only sigma b will be there and this shear stress tau 1 plus tau 2 will be there. Now, if a state of stress is in 2D case is like in plane stress case, you can say is like this, then you can say our maximum shear stress we can write as, this will be, you can say sigma x minus sigma y by 2 whole square plus, you can say tau resultant square. So, here you know only one normal component is there, that is sigma b. So, this sigma is actually normal stress and tau is shear stress, this you should keep it in mind. So, here generally only one normal stress is there, that is why sigma b, that is sigma b, that is why sigma b by 2 whole square is there, and resultant shear stress here we are getting as tau 1 plus tau 2, this you should keep it in mind. This is the difference. So, this will give us a value which is look like what is sigma b, and last slide already I have shown. So, sigma b equal to 1018.59 by 2 whole square, and tau 1 also we know 63.6 divided by t, and tau 2 we got as 636.36 divided by t. So, this whole square, correct. So, you see these tau max we need to equate with permissible shear stress, or you can say sigma p, or you can say this is also called allowable shear stress, which is given as 100 Newton per millimeter square, Newton per mm square. This left side also it is Newton per mm square. So, from here generally we will get T is equal to throat thickness will be equal to your 8.66 millimeter. So, we need to find out the size of the weld. So, size of the weld you can write as A is equal to your T by 0.707, you know very well, because if two perpendicular welds are there generally it is like this. So, 8.66 divided by 0.707. So, this will give us a value which is equal to 12.24 millimeter. So, you can consider this is little bit higher side for design purpose 12.5 millimeter, or you can consider 13 millimeter next higher digit, but 12.5 millimeter also will be in safe side, not less than this size, this you should keep it in mind. So, you can see in previous case we observed that once a beam is subjected to a transverse load 10 kilonewton, then our size was we got as 7 millimeter, whereas if it is subjected to a torsional moment, then you see this size increase from 7 to 12.5 millimeter, that torsional moment if it will be 2500 Newton meter. So, you can see, so depending upon the loading types and its combining effect, it designing procedure changed, as well as you can see your its dimension of the weld also changed. Okay. Now, we will discuss a very important method which have a wide application, you can say in the field of welding related structural design. I am now going to discuss in details about that method. So, that will be also required for finding out the design dimension of a welded structure, as well as let us you have done some welding in a particular structure, whether that welding is sufficient for those types of welding structure or not, to estimate those types of information also, these techniques will be very much helpful. Okay. That is why I have written here, this is a very important method, especially for design of welded joints subjected to combined load. So, before going to discuss about these techniques, first of all, till now we have already got the throat area, then throat thickness also we got. Generally, if a flat weld where the two, in case of means flange and wave, which are perpendicular to each other, then what happens in this case, generally we got that the throat thickness is this, and here generally we got our throat thickness T is equal to, if this is our leg length is W or H, whatever it is. So, then throat thickness generally T is equal to, you can write as 0.707 into W. How it is coming? I have already discussed in details in last lecture, because sin theta equal to generally T by your leg length. So, from generally here sin theta equal to 45 degree if it is, then generally there we used to get T is equal to 0.707 W, because if this is your theta, theta, then you can write as sin theta is equal to T divided by W. Based on this relationship, generally you can get the relation between T and W. T is the throat thickness and W is the what it is called leg length. Now, for fillet weld, if these two component joined together, if it has a angle between these two faces, if this angle, this is the angle, if this angle between these two fusion face, because this is one fusion face and this is another fusion face, I have already written here. You see, this is one fusion phase, this is another fusion phase. That means the angle between this fusion phase and this fusion phase, if this angle is varying from, generally it is considered according to some standard, international standard. If it is varying, this angle, if it is varying from 60 degree to 90 degree, there generally we consider that your whatever the that means throat thickness equal to your 0.0707 into WE got, this let us consider this is your alpha. So, this alpha into W let us consider throat thickness equal to alpha into W. So, in case of fillet weld, generally depending upon this, you can say fusion faces angle, this alpha can have a range of value. What I am telling, understand, because you see this alpha that is provided by some international society. You can see if the angle between 60 degree to 90 degree, then we generally used to get a value of alpha which is 0.707 we can consider. If the angle is more, means let this is one specimen and this is another specimen, So, in this case, if you do the fillet welding here the angle is more than 90 degree, here you see more than 90 degree, here theta is more than 90 degree. So, if the angle is 91 to 100 degree, then generally this throat thickness is reduced, so alpha also is less. You can see this 91 to 100 we generally used to consider according to a standard, some international standard, that standard that is 0.65. If the angle is further more 107 to 113, then this value will be further reduced to 0.55. If it is further increased, that means if this theta value is, greater than 114 to 120, generally this alpha value, you can say this whatever the alpha value we consider, that 0.707 in case of 90 degree case, this alpha value generally further reduced to 0.5. This you should keep it in mind. So, here generally throat thickness T we consider as alpha into W. So, depending upon the fusion phase angle, what is fusion phase? In this diagram it is clearly mentioned. This is one fusion phase, this is another fusion phase. Okay. So, this angle, this alpha value is varying. So, this is generally based on this relationship, whatever the throat thickness we used to calculate, that is known as effective throat thickness. This you should keep it in mind. Okay. Generally we use this effective throat thickness for our design and analysis purpose. This you should keep it in mind. Now, this is for fillet weld, but in case of butt weld also there is some standard we need to follow. Like let us consider in case of a butt weld, if you join two plate, let us different thickness plate, and if you have done this butt welding here. So, always you should keep it in mind, in this case you need to consider your throat thickness T will be equal to, let us the thinner plate have a thickness T2 and let the thicker plate have a thickness T1. So, here throat thickness T should be considered as thickness of the thinner plate, this you should keep it in mind. This is another concept for designing of butt weld. This is for butt joint. Okay. Now, if full penetration is there in this weld, then generally we consider T equal to T2, that means lower thickness of the plate. But some cases, if the penetration of this butt weld case is not full or incomplete penetration of butt weld is there, in this case generally this effective throat thickness we consider as 5/8 times of the thickness of the thinner part of that joint. This you should keep it in mind, that is 5/8 times. So, in case of incomplete fusion, you can say or dissimilar thickness of plate, if we do the butt weld and there will be say let us incomplete fusion, that means let us at root side there is some fusion is lacking, what I am telling understand, that means at root side a fusion is not taken place, that is incomplete types of fusion. In this case, let us this thinner plate have a thickness is T2 and thicker plate have a thickness is T1. So, here generally T throat thickness here I am writing T is generally considered as 5/8 into T2, this you should keep it in mind, because this will be considered for designing of welded joint. This is called effective throat thickness. So, for different angle of between fusion faces, what should be the fraction of leg length is equal to a throat thickness, I have already discussed by using this table, as well as for butt weld cage also I have already discussed about throat thickness concept, that is called effective throat thickness. Now, we will go to discuss about the concept of shear flow.